All right, so we're looking at least square regression. Again, this is another topic where I don't so much want you to get bogged down with trying to calculate it. Just know where to go to calculate it and to understand what it means for a data set. So this is least squares regression. And so in the previous lesson, we were just eyeballing it. We were looking at points and going, oh gosh, this is where the line, I think it might be. But there are actual formulas and ways to figure out where the exact perfect line is, because maybe if I was given a data set, I would draw one line, but someone else might draw another line with a different reasoning. There is actually an exact perfect line. And that line is called the line of best fit. It's the best fit to that. The way that we do it is we actually called least squares regression line. So the reason you call it least squares is you're actually going to find the distance from the line to each point. And then because some of them are going to be above and below in all these different examples, you want to um, not worry about if it's positive or negative or above or below. You just want the distance to be as little as possible. So that's why we actually square it, is to get rid of the positive and negative consideration. So you square them because a positive squared gets a positive, a negative squared gets a negative as well. And then you add all of those up and you're looking for a line where all of those numbers come to a maximum. The distance between the line and that point, actually, when all of the squares are added together, it is the least value it could be. If I put that line somewhere else, like here, I'm going to end up with a way bigger, when I add up the squared values, it's going to be a way bigger value. So you're looking for those least square regression lines. So that's what it's called. Again, so in this case, you'd see like this point is 1.1 below the line. This is 1.6 below the line, 1.5 below the line, 1.4 below the line, and then our two that are above, you might be thinking, oh, there's 4 below and 2 above. That doesn't work. Well, it actually does work. Because you want to balance it, but it's not about necessarily getting 3 above and 3 below. In this case, since there's 6 points, you actually are looking for those squared values to be as little as possible. So by putting 4 below, but if you notice there's smaller values, it's going to be counterbalanced by the 2 above, which actually end up being a little bit bigger values. So it's all a balancing act. So if I moved that line anywhere else, the sum of all the squares would actually be bigger. So this particular line happens to make the sum of all the squares be the least it could possibly be. And we consider that the line of best fit. So there are a few ways. This is an awesome website that I have found that basically just does the entire thing for you. And I will include a video. I don't know if it's going to let me click on that. Nope, won't let me click on that. So I'll go ahead and include that video of just how to use that website. And then you can also use Excel. So again, I'll include the video there. It won't let me click on this in here. But yeah, there's a video there for that. Moving on to residual values, this is the practice test. I believe it's 309. So residuals are the differences between the real point and where the line of best fit estimates the value. So these values right here are the residuals. So negative 1.1. If they're below, you'll see that they're negatives. And if they are above, you'll see that they're positive. So that's one thing to note. Below the line gives you a negative, and above gives you a positive. So your goal is always to kind of like balance out the residuals. So you want to have a balancing between like negatives and positives. If you had all positives, then that means you've placed your line in the wrong spot. So, and another thing to note with these observed values, when you're looking at this, the points are the observed value. So it says when x equals 6, so that's over here, whoop, the observed value is the actual point there. So the observed value when x equals 6, come over here to the y-axis, would be 4. So observed is the point itself. And then y hat, that's the line. That's the point determined by the line when x equals 6. So I'd go over to 6, up to the line, and I would estimate there. So this looks like it's a little shy of 3.5. I don't know, maybe 3.4, somewhere around there. So again, y hat means the actual position of the line, whereas the observed value is the location of the dot itself. So the residual would be the difference between those two. So I said we had 4, and then minus, if I said the line value was about 3.4, I would subtract those and you would get 0.6. So the residual for that point is 0.6. And if it helps, I'm going to go through. These ones would all be positive. Oop. And then these ones down here would be the negative ones. So if you count them up, if we were to count up, there's 1, 2, 3, 4, 5 above, so 5 with positive. And then we've got 1, 2, 3, 4, 5 below. Again, it won't always be exactly 5 and 5 or 3 and 3. The exact distance actually does matter as well, because if you have 4 below, like in the previous problem, that are closer, that is counterbalanced by 2 above that are further away. So it's not just having positives and negatives, it's also about how big the positives and negatives are as well. So the residual for that point there is 0.6. All right, so the table shows the various ages of some plants, their observed heights, and what their predicted heights were based on the least squares regression equation. So observed, this is the dot. Ooh, I don't think yellow is a great color there. So this is the dot. And then predicted, that would be the line. So this is the line. Okay, so what a residual plot is, you are going to subtract dot minus line, and that'll give you the residual. So I'm going to go dot minus line, so observed minus predicted, and so that's 0.3. And then 3 minus 3, that's 0, so that's a good one. My line happens to go straight through the point there. Let's see, 6 minus 6.2, so that's negative 0.2. 3 minus 4.2 is negative 1.2. We've got 3.5 minus 3.4, that's 0.1. Make my point a little more obvious. 6 minus 5.4, that's 0.6. 4.5 minus 5, that's negative 0.5. 4 minus 4.2, that's negative 0.2. 7 minus 6.6, that's 0.4. And last one, 6.5 minus 7 is negative 0.5. Now the way we would plot these is we actually would put a horizontal line, and then you actually plot the x value, so like 2, but the residual is 0.3, so I would plot it at 0.3. And then, and let me do that in a different color, like a lovely blue, there you go. And then, you know, 4 would be right here, and its residual was 0. And so I would put its dot right here. Let's see, and if I called that 0.3, then 1's probably right about there, and then there's -1. Okay, it's a very, very tight little graph. Let's see, we've got 5. Notice they're not in numerical order here, just to be tricky. So 5 would be right about here, and its residual is 0.1, so that would be somewhere around there, and so on. So you would plot all of these. So when you look at these options over here, and remember it says exactly 2, so you would look for at 2 is the residual -0.3. At 9 is the residual -0.5. At 10 is the residual, so here's 10, 0.6. And at 14 is the residual 0.5. The sign does matter. So 0.5 is not the same as -0.5 for these. And the table shows, same table, which statement is true. So your balancing act with these is you want, when you draw that residual plot, you want some above and some below. You don't want like all of them to be below, then you placed your plot in the wrong place. So you don't want all of them below. You want a smattering. I don't know a better word than just to say like a smattering of them. You want some above, some below, something like that. So a line is a good fit for the data because the range of the residuals is small. Doesn't necessarily mean range is going to be small. You mean you could really have a big range. That doesn't make it a bad line. It makes it less correlated data, but there still is a line that fits every set of data the best. It's just not a well-correlated data set. Let's see, a line is a good fit for the data because the points in the residual plot are scattered. Let's see, next one says form a pattern. You don't need a pattern. It's not like you should be going like alternating. It doesn't have to alternate. So there isn't necessarily like a pattern that needs to occur, just the fact that there should be some above and some below. But you might have like, for example, let me erase all that. So all the dots, let's go in white. There we go. I mean, you could have like 2 in a row above, below, above, below, and then like have below. That would be just fine. You could have it be in a different color. You could have like an perfect alternating. There isn't a pattern that needs to occur. Anything really, as long as you have them above and below. So line is, oh, I read that, sorry, it says poor fit. Okay, so to clarify with that one, just because they're in a pattern doesn't make it a poor fit. A pattern has no bearing on if it's a good or bad fit. A line is a poor fit for the data because one of the residuals lies on the horizontal axis. That is actually good. If the, which one was it? This one right here would actually be on the axis, and that means your line goes through a point, and that is not bad at all. So it would not make it a poor fit, so I'd say that's a no. All right, the password is Riley. Have a great Friday.